All right, we're going to start on chapter 2 today, and I'm recording this video to kind of help augment what I already have recorded in the Python course shell. When I taught this last time, I was kind of pushing a lot of the concepts by using the PowerPoints, and I decided subsequently that I really didn't like the author's PowerPoints as much as what he had, he or she actually, I'm sorry, in the book in terms of the presentation of material. And so subsequently in the course, when you look at lecture videos, you will see that I often just kind of step through the chapter. And to me, that works better than the PowerPoints and really kind of helps you also, in my mind, help you understand the readings better at the same time. So here are the chapter goals. We're going to look at a lot of really important programming concepts in this chapter because they're fundamentals. So we're looking at these things called variables and constants, floating point numbers, how numbers and stuff work inside of this environment. A little bit different than a lot of other older languages. Why comments are important in code, how to write mathematical expressions and assignment statements and the difference between those two things, because often they look the same. To create programs that receive input from the users and then put something back on the screen. How to work with strings or basically text in a program. And the last one is not something that I'm going to focus on, but however, I will tell you guys, the focus of this class is not to teach you GUI programming. We're teaching you more the programming concepts. However, if you want, like each of these chapters will have little graphic exercises. You can learn those on your own if you wish. So just keep that in the back of your head as you're working. The reason that we don't spend time on that is because we feel that if we spend too much time teaching you that right now, we don't get to some of the more important advanced concepts at the end of this course that you need to move forward in your other programming. But if you're, I know at least a couple of you are in the data analytics program. In that program, we do cover GUI programming in Python. So we pepper that into our courses. So as you take more advanced data analytics courses, you will start to pick up those skills. All right. At the beginning of each one of the chapters, they do this like kind of listing of all the little topics and stuff they have in the chapter, so you can jump right to them. And I always find this a handy little list. So if you're ever kind of navigating around and want to get the stuff quickly. I really like the ebook format for this author. I think that it works really well and it's pretty flexible. So kudos to them for doing a nice job on it. All right, let's talk about what a variable is. And so here it says that, your computer is like doing stuff, and whether you're getting input from a user or you're calculating a value, sometimes you need to kind of hold on to something for a second before you take the next step. And what we do in Python is we create variables to store information. So basically it's, the analogy that I've always used is I think of a box, right? And that box, okay, well, it starts out empty, right? And I can put stuff inside of it, right? But usually, if I put something in a box, I can't really tell what's inside of it unless I give it a name. So I'll take the box and I'll name it and say, well, this is, maybe this is total wages or something. And I can put stuff inside that box and then it's stored there. And whenever I need to pull it out, I can retrieve it by calling it by name. So I always think of a variable as kind of like a storage location that has a name, and you can do stuff with that storage location. It's one of the most powerful things that we do in programming is the ability to store information and then recall that information. And that's done by virtue of working with memory spaces. So actually, when you create a variable in a program, you're really reserving a portion of computer memory to store information. That's what you're functionally doing. When the program stops running, that memory is released so other programs can use it. All right. So he often gives a lot of like, interesting little examples. This one I'll skip over, but I think I kind of mentioned this already. So a variable is a storage location in the computer program. Each variable has a name and holds a value. Absolutely true. So he has this little example here of assigning a value to a variable. So one thing, let's start with this. If you're going to store a value for something, what its name is should really describe what you're storing as much as possible. Now, the old-fashioned approach is sometimes we would not have as many characters to work with for whatever reasons because of memory limitations, and we'd come up with these short little names. But I always tell students, be verbose in what you name things so that you know exactly what you're looking at later in your code. So in this case, they're setting up a variable to indicate the number of cans in a six-pack, basically. So instead of just calling it cans, he's saying cans per pack. So it's a little more descriptive. And then there's an equal sign. And on the right side of the equal sign is a value. Now, on the right side of the equal sign, that value could be a number, or it could be text, or it could be something else. And the other something else could be something that's a more complicated structure, but we'll get to that. But for now, we start with numbers. Numbers are one of the easiest ways to start. And the way that you always look at these, what we call an assignment statement, is that equal sign tells you that whatever's on the right-hand side of it is being placed into the thing on the left-hand side. And that, fundamentally is true in just about every programming language that you work with. And this does not imply math. And that's a really important distinction, which then should raise the question in your head, well, then how do I do math, right? There's a different way, and you'll see the result of it. But the equal sign always implies that you're assigning a value to whatever's on the left. Value on the right, stored in the container on the left. Now, if that number is stored in here, now if I want to print the number 6 on the screen, if that's ultimately the goal, I could just say print, quote unquote, 6. I could put quotes around it and print it. Or I can call the storage location, which then extracts whatever's in it and prints that, whether it's a text or a number. So that is a pretty powerful little thing. If we went ahead and changed that value in a later statement and said, well, there's now 8 cans per pack, and then I ran this command again, then it would output 8. See the difference, right? So you can establish a value for something, and then as you go in the program, you might be changing the value. So like I think of, like, I walk into a lot of stores now to go shopping, and they have like limitations as to how many people can be in the store, and they have somebody at the store with like a clicker or an app, like one person out, 2 people in, or whatever, and they're keeping track. And that's the same thing that a variable does. So it keeps a running total, whether you're adding to it or subtracting from it, if you're working with numbers, or if you're changing what words are being stored inside of it. So they have these little side examples here. So, all right, here, you set up the variable name, the value, that goes inside. So cans per pack is 6. If I switch it to 8, now it's 8, it just changes. Once again, another little example, and this is what's cool about this ebook, right? Because this is the first assignment, the variable is created. So the variable doesn't pre-exist until you give it a name. This is a little bit different than some programming languages where we have to formally declare what type of data it is and initialize it. Python is a very flexible language. You can functionally skip that step. But the moment that you name something and assign it a value, it exists, is basically the point. Here, it says the variable is initialized. So they're putting the 55 in there, right? Now they print it, right? So it comes out. In the next statement, they're storing a different value inside of it. And then when you go to print it again, you get a different output. So this is what's cool about the ebook, is it has all these little tools built in, and I don't often click on them, but I am doing it now just to kind of demonstrate it for you. So feel free to play with that. I think they're pretty darn neat. The author usually provides, these little reference boxes too, just kind of as a review. And this is more in a code sense. So here, very often, if you create a variable and you don't have a value to put in it yet, but you just create it in advance so that you have a place to put something, often you might set it to 0, some arbitrary amount. You know, for a total, right? You know, you don't want to walk into the store with a total of $100, so that, you know, it's better to start at 0. And then as you go, you can add to that total. So in this case, they're doing something a little bit different. So these are, hypothetically, let's say we had other variables in our program that were predefined with values. We could take bottles and then multiply it. This is a multiplication symbol in programming, by bottle volume to come up with our total. So we can actually take a mathematical expression, and the result of that mathematical expression will get stored here. So whatever that math works out. So if this was 5 and that was 2, we'd have 10. Now total would be equal to 10. We can also do what we call, you know, adding to the total one, not changing what was previously there. So if I already have a pre-existing amount in here and I don't want to delete it, I would include adding the original total back in. So this is where it kind of becomes a little bit of a mind bender for people that have never programmed before. It's like, wait a second, I can take what I have stored, add it to the equation and put it back into itself? Yes, right? So for example, if I had 1 person in my store and then 2 more people walk in, I now have 3, but to get that, I have to pull the 1 out that I already have stored, add it to the 2, and then get 3, right? So often you see, you know, basically almost like self-referencing, and that's allowed in programming because this will be the result of this. So it will start with the original stored value and then become the byproduct of the statement. Okay, but the concept that everything on the right feeds into and gets stored here, or the result of everything on the right, in this case, the result of the math, will get stored inside of the total field. I can see my kids are awake. So I'm playing Terraria. All right. And the author goes through, the assignment operator does not denote mathematical equality. So we are not saying that these values are equal. It's called an assignment statement. So we're assigning the value on the right to the storage location on the left. You know, I think that covers this topic pretty well. But if you, you know, the example is, you know, for this little equation here, if you already have 8 stored here, right, in cans per pack, and add 2, then cans per pack becomes 10, right, ultimately. They have a couple of examples here. You can see I've already done these to demonstrate to students, but you can play with these. You can also click start over. It kind of keeps track. And maybe you guys can tell me, is this a valid statement? Can cats equal 3? Sure, why not, right? We're just taking that value and putting it in cats, right? And I like it that it gives you this like little output here. So how about this statement? Can cats plus 1 equal dogs? And so it shouldn't say dog. Now, Robert, you're shaking your head, right? But hypothetically, if cats has the number 3 in it, and I add the number 1 to it, what's inside of dogs? Wait, I can't have a cat inside it. No, that's not the way you think about it. It's just a value, right? That it is totally, yeah, that's a completely valid statement. What they're trying to do is throw you off by giving you different variable names. And it's not about what the variable names are, it's about what's stored inside of them. Now, if this was words that were stored inside of cats instead of number, then it would not be valid. Okay. How about this one? Parakeets equals parakeets plus 1. Well, we just talked about that, right? That's completely valid too, right? Oh, except it says, wait, oh, it must have been predefined. So the error here is we didn't predefine the value that's inside of parakeets. So if I would have even said parakeets equals 0 or parakeets equals 1 and then used it, it would be okay. An epic fail on the teacher's part, right? But you know, here's the beauty of computer programming though. Hey, oh, it's wrong. Okay, well, let's fix it. You know, so remember, IT always has the undo. How about this? Is this valid? And the answer to that one is it's not valid. Yeah. So in other words, on this side of the equation, I can have variable names or I can have hard-coded numbers, but on the left-hand side, it has to be a storage location. A number is not a storage location. Okay. Can goldfish equal cats? Well, based on this one, if we haven't predefined it, I would say no. However, if cats was predefined, which it was up here, we should be okay. So I'm going to assume valid. So we're okay. See how that works? If cats hadn't been predefined though, so we could have used cats, dogs, I guess not parakeets because that wasn't valid, and not hamsters because apparently that was not valid either. So hopefully that's helpful for you guys. Play with those little exercises though. The fact that they're interactive like that, I think is kind of a fun little thing. Right. Python, like many languages, you know, really are centered around mathematics. You know, you really can't do programming without understanding math to some level. You don't have to be, you know, a calculus expert, but, you know, I would say like algebraic math at the very least is important in understanding that. And Python deals with what we call data types a little bit differently than a traditional programming language. So if I was writing a program in Java, now, given that this is a first semester web class and a first semester data analytics class, my web students would also be taking Java 1 at the same time. Now in Java 1, if we want to declare a variable and make it a number, I actually have to tell it to be a number. I can't just use the name like what we saw on the previous screen. So in Java, I would say, well, if I want an integer or a floating point number, I would do a little prefix and I would say int, give it a name, equal sign, and then give it a value. In Python, it doesn't care. So that's really bizarre. The only other, well, I shouldn't say the only other language, but the other real popular language that you might learn that is the same way is JavaScript, where JavaScript also doesn't really care what data type you're using. It dynamically adjusts, and that's what Python does. Part of that is the fact that this is what we call an interpreted language as opposed to a compiled language, so it doesn't actually turn into machine code. It's just executing a set of instructions. A compiled programming language takes whatever code we write and converts it into ones and zeros to store it as an executable that can then be run again and delivered as an executable. Users cannot see the source code. People cannot adjust that source code. It's kind of locked. And Python gives you the capability to do some powerful things as a result, because by not declaring a data type formally, it gives it flexibility to actually change dynamically from one data type to another, which you can actually leverage to do some pretty sophisticated things. For the most part, though, whenever you're working with a number, you're going to want to keep it into a certain way. Now, despite the fact that we're not doing formal declarations, so if I look at a language like Java or C++, you know, like, or old-fashioned C or one of those, declaring the data type is really important. In fact, most of those languages have not only the two numerical data types that Python has, they have sometimes as many as a dozen, you know, and with different capacities. Some of them are for scientific notation, some are for floating point numbers, some are for very, very large numbers, some are for very small numbers, and it's all about how memory is managed. So if you know that you're only storing a number between, like, I don't know, 1 and 100, you don't need a numeric data type that can hold 10 billion. There's no point, you know, and every time you're declaring it, you're taking up all that storage space at the same time. So in old-fashioned languages, you have more granular control. In a modern language like Python, the language intelligently does the memory management and what we call garbage cleanup in the background, so that it only is using what it needs to use without wasting a lot of extra memory. Traditional programmers get a little uncomfortable with that flexibility because they learn such rigid systems, but I think it's kind of cool because this is, I think, more the wave of the future for sure. All right, let's talk about the different number types now. let's start with an integer. An integer basically, folks, is what we call a counting number. So 1, 2, 3, 4, 5, like as a kid, what you first learned to count, you don't think about like 1.75 or something like that. You just think of the whole number, a counting number. That includes positive and negative numbers as it is indicated in the chart. So an integer has no fractional part. It's a whole number, positive or negative, and 0 is also an integer. So it's part of that whole thing. When you start to create fractional numbers or numbers that are, the in between the counting numbers, then by simply including the decimal point, Python understands that it is now a floating point number as opposed to integer. Other languages, if I try to put 0.5 into an integer, it would just break. It wouldn't even let you do it. Python just says, oh, you're just switching. Okay, you're good. and that's kind of an interesting flexibility. So anything that has a decimal point, so 0.5, 1.0, and the decimal points can be much larger than that. That's just an example of that. Now, the one thing that should, if you're thinking about math at all, you look at a number like this and go 1.0, and you should say to yourself, isn't that the same as just saying 1? Yes, it is. However, by including the 0.0, we're telling Python that it is a floating point number, and in some cases it changes the output of the calculations so that whatever numbers you're interacting with also create more detail. So for example, if I do division with 1 versus 1.0, I might get different output, and sometimes that different output can make a big difference in your program, and that's why it's important. There is also the possibility of doing exponents, and this is what Python does. They include the e, right, to indicate that would be 10 to the 6th power. And if you've studied your mathematics, it just basically is another way of saying 1 million. But that is a notation that's used often by scientists. Python does support it. That's actually a little bit anomalous. Most other languages, formal languages, don't usually have to run special tools to do that. You can also have floating point numbers that have a decimal point and a negative exponent as well. So that would mean that it's over that number of zeros, and actually you're really creating this number by doing this. Where that becomes important is if you're doing like high-end scientific calculations or data analysis, and you're looking at like micro percentages and things like that. And it's easier to express it this way than necessarily to, especially if like it's like 20 digits long or something. They show a couple of errors, so you can't put commas in there, right? That won't work. That's just a formatting thing. And if you want to say 3.5, you can't do that either. You got to say 3.5. Okay. So a couple of little examples. Says Python can store a value of any type. And it says the data type is associated with the value, not the variable. So notice how tax rate in the first statement is just 5, right? Here in Wisconsin, that's our formal tax rate, even though some counties have more. But yeah, you could just say 5%. However, I could take a floating point number in the aftermath and stick it inside the same container, which I guess I've kind of been talking about. And Python is very okay with that. It'll just say, okay, we've switched data types, no big deal. And to take it even a step further, you can do what they're doing in the third step, where it says not recommended, and switch it to text, and it still will work. Now that's kind of like traditional, people that have learned programming from days past go, oh my God, what are you doing? No, you're destroying things. But Python actually allows it, although you notice the little comment, it's not recommended because you're just kind of polluting the water. So what they're suggesting is you intelligently know what you're storing and what format it's in and why you're using it. And that, so basically, even though it's flexible, the recommendation is to stick with, traditional programming techniques and keep things the way that they are. I have seen, like I mentioned before, some programmers actually leverage that flexibility of what the variable can hold to do some really crazy sophisticated things. And I've seen, so you can, as a guitar player, you guys, it's like having a really cool effects pedal and you get to play with it and you can kind of do stuff that never has been heard before. So I think that's helpful. The other tip that they give here, as I mentioned before, again, and I think this is a good example, is even though the tax rate is 5%, in many cases, they would recommend that you list this as a 5.0, because when you start to multiply it against dollar values, which always have 2 decimal places after it, the math will calculate correctly, where some cases a straight 5 will not. You'll see the result when you start to do some math. All right, I'm going to move on to the next thing, which talks about how to name variables. So there's some conventions in naming variables, and one thing I already mentioned was be verbose in what you're creating, so you know what you're looking at when you come back to it later, maybe even years later. But there's some things that are allowed and some things that are not. And some of these are common for some languages, and some are kind of anomalous. But okay, so it says names must start with a letter or an underscore. Right, some of you might wonder why an underscore. Well, that's actually a convention that a lot of programmers use to indicate certain types of content, which is why that's allowed. Other languages will sometimes also allow like weird characters like $signs, for example. But it has to start with a letter or an underscore. Notice it cannot start with a number. Okay, so it says, now after you get that first character, the rest of it can be letters, numbers, or underscores. You have a choice. Okay. You cannot use symbols such as dollar signs or percent signs or ampersands. You cannot use those in variable names because sometimes those characters have special meanings in the language. Spaces are also not allowed. You can use upper and lower case. And in fact, this little format that you see here is what we call Camel Case. That's why they have the camel here. So the thought is you start with naming everything lowercase, and every time you have like a logical word change, like you're squeezing like 3 words together, every time you start a new word, the first part of it is capital. Some people will use underscores instead. It's just a preference, but that technique is called camel casing. Right? Names are case sensitive, so if I name something like this is can volume with a capital V, and I name this one with a V, and then I try to use them thinking that this one is the same, they are different. Different names, different containers. Yes, 1 capital letter makes a difference. So those are unique variable names. And be careful with that, because that's a common mistake when you start out. And then there's also certain words that are built into the language that we're not allowed to use. So in here, for example, they're saying that like if is a reserved word or a keyword in the language, as is the word class. So I can't call my variable that because it thinks you're trying to do something else. And they do have, this appendix here, you can click through and go to it or flip to the back of your book and take a look of all the reserved words that Python has. Typically you don't run into them, but every once in a while you'll pick one going, hey, I'll call it class. Oh, because I'm doing like a student thing. Nope, not going to work because that's a reserved word. They also have some tips. And one of them I already gave you. It's better to use a descriptive name than a terse name. So like if you decided to abbreviate cans per pack to be CPP, you're going to come back 5 years from now and go, what the heck is CPP? And that's kind of the point here. In the old days, people would do that all the time. And programmers would actually, frankly, do it. They would have their own abbreviation schemes so that if other programmers came in to kind of try to fix their code, it would take them a while. And it's called job security. Like a lot of programmers would protect themselves that way by not describing stuff so that people would really have to do a lot of time figuring out what the heck they meant. That's considered uncool these days. It's always considered to be verbose. And if you are using abbreviations, it's also considered polite to put a comment in your code that indicates what it means. In fact, I would do both, honestly. Okay, so in some instances, you're going to see some of this, and we're going to come up on that, I think, pretty soon here in our material. But there's this convention in programming where, like, if you start naming variables basically as all uppercase with underscores separating the words, that implies a constant, which is a variable that has content that hypothetically cannot change. We'll talk about that later, but so if you ever see that, it's not that it's not a valid variable name, it's just indicating that it's a constant. All right, let's move on. You guys can do these little self-checks and stuff all on your own. And here's constants. All right, so traditional programming, once again, if I had a value that I used in a program that I know would never change. So let's say, you know, thinking of the cans per pack, let's say that, you know, like a can of soda is 12 ounces, right? And it's always 12 ounces. I could write, you know, the number 12 in here and give it an all capital name with an underscore separating the words. And that indicates whoever's using the program that this value is not intended to change. And I want you to listen to what I said there. It's not intended to change. When you learn Java, for example, or C++ perhaps, you would actually put a little modifier at the beginning of a statement, and usually const, constant, which forces that variable to not be able, it actually locks it in like a proper programming language. Once you declare a constant, that value is not changing. There's nothing you can do to change it. With Python, we do it more symbolically. So this is still just a regular variable. The value can actually change. We're just saying that just by convention of naming it with all capitals, that we're not going to try to change it, if that makes any sense. So the convention is if you name something with all capital letters with those underscores between the words, we're assuming it's a constant and the value is intended not to change. So I think that's probably about as much as we should say on that. All right. The other thing that we often do when we write code is we'll end up in the situation where, you know, we want to understand what we did when we were writing that code, or we want to understand what this means when we're writing the code. And notice here, comments in Python programs can be added in a number of different ways, but it's not uncommon if you have like a piece of code. Notice how we start with a pound sign. When you put that pound sign into Python code, it tells the interpreter that's reading the code inside, you know, your program to ignore anything that's listed afterwards. So it's saying, you know, yeah, that's just here for me. It's like kind of like notes in the sideline to give me a clue as to what's going on without affecting the operation of the code. So you can leverage those comments to kind of like put notes in your code. And so then when you come back to it, you understand what you meant. In fact, often I tell students, like, if you're writing, you know, a more complicated program and you're trying various solutions, you can try a solution instead of deleting it and trying a new one, just put comment marks in front of it. What if maybe you weren't that far off and you can come back to it, it's still there, right? But more often, what programmers use this for is to kind of document a program. So for example, in this little, right here, they have, you know, series of pound signs, and you'll see that what they have there is kind of a description of what the program does. And there are conventions in some languages, and depending on the employer you work for and what you're building, that they'll always ask you to put comments in. You know, it's like, if you're building a giant application, chances are you're working with people who are working on small pieces of the puzzle independently, and then somebody stitches them all together. So your job might be just to create this one little piece of code and then hand it to somebody else. Well, wouldn't it be nice if there was notes inside the code that told the person what this is all about and what is happening? And that's the point of it. But you'll often see this kind of a thing. Another thing that I do often when I'm writing code, especially if I have a set of instructions, is I'll copy that set of instructions, paste it into my code as a comment, and then I don't have to flip back and forth between, you know, my book and the other thing. And then, you know, it also is kind of nice. It's like, you're basically breaking down the steps. So like line 6, you know, it says liters in a 12-ounce can and 2-liter bottle. You know, so a can volume is 0.355 milliliters, or liters, and a bottle volume is 2. You know, and you're giving a description of what and why. Once again, comments are so useful at documenting things and helping figure things out in the aftermath. Always better to have more information than less. The engine does ignore it. So like if I run this code, this stuff that won't appear on the screen anyway. It affects nothing that runs. It's just information. So comments are extra information you put in there. All right. I love these little sections that they drop in here to provide extra information. So here, for example, talking about common problems, I think we already kind of saw one of these where they're trying to use this variable liter per ounce in a calculation, but it hasn't yet been defined, right? And so that will throw an error message. So make sure that you predefine the variable. Any programming code is always executed as a series of steps from top to bottom. So you guys wonder why I had you like do a recipe and a flow chart? Because you have to follow an order. And this is a perfect example. So I couldn't do this calculation with the definition of liter per ounce below, but if I moved it above, it would all of a sudden work. And that top-down hierarchy is important. You know, it's like if you're making the cookies, you can't bake them before you mix the ingredients together, right? You don't like bake and then mix ingredients, and that's kind of the correlation. I think I've already been saying this a lot. You know, like CV doesn't say can volume like can volume does. So be verbose and specific in how you name things. They also talk about this concept of a magic number, and it says it's a numeric constant that appears in your code without explanation. So for example, total volume equals bottle times 2 is Y2. Are bottles twice as voluminous as cans? Now, what they're trying to tell you here is really what they're intending to do is actually multiply the number of bottles by whatever the volume of a bottle is. And they're saying to you that in some cases, instead of just hard coding that 2 in there, you're better off defining what it is and then using the definition of it or the variable holder to do the math as opposed to hard coding the number. And yes, a lot of programmers do hard code the numbers in because it works, frankly, right? And it's not going to change. But let's just say, I don't know, our president all of a sudden says that 2-liter bottles should now be 2.5, right? And you would have to go back into your code, find everywhere you have the number 2 and fix it, you know? Or because I'm using variable names, I would just come here, change it in one spot, and the whole program fixes. And you see like the convenience of that and the logic of that. So if you have a value that's used many times over and it represents something that you're going to utilize over and over again, name it, give it a value, and then when you need to make a change, you're making the change in one spot. And it becomes very powerful. All right, moving on. And then this is the one, you know, where it's like, oh, geez, I have to do math. Yes, you have to do math, you know, because you're a programmer. But, you know, most programming languages are built to do math. And it's really, really important. However, when we do math operations in the programming language, it's different than writing it out like you would algebraically, you know, or, you know, as you learned in school when you were a kid. So for example, when you probably first started learning algebra, you would probably see like an equation like this, where you have a couple of variables, see the correlation there, right? In math, we call them variables too. They're unknowns, and you can have addition, a divider line, and put it over 2. We can't type that on the keyboard, right? So the best we can do is take the A and the B, put them inside parentheses, because that's one expression, and then divide that by the number 2. So we'll talk about all the symbols soon, like right now. So this is what you get when you don't practice, Robert, right? But the symbols for doing the basic math operations are, I think, are pretty intuitive. So plus or minus or plus and minus. Instead of like an X for multiplication, we use the asterisk, which is the shift of the number 8, and then the forward slash for doing division. And those are the four basic operators. You can do math on both variable names and on hard-coded numbers, absolutely. But we still have to follow the order of operations of math. Does anybody know what that is? There's like a little acronym that people would use for doing the order operations, Charles?
Parentheses, exponent, multiply, divide, addition, subtraction.
Correct, right? And there's the acronym is PEMDAS, or please excuse my dear Aunt Sally, or something like that, right? And the point is that, you know, how you evaluate things. So in other words, if I would have wrote this expression without having the parentheses around it, the order of operations would dictate that I would have to divide B by 2 first and then add A, which can give you a very different result than the intended add these together and then divide by 2. Now, this goes back to kind of math things. I always tell students, if you're not sure, put the parentheses around what you know should be together. And it's very often kind of dictated, but just good to know. Right? And they walk through why that works and why it's important. Normally, if we were in a longer class, I would actually run through some of those little things, but try those math things yourself, if you would. All right. Now, Python also has this capability of declaring exponential notation right inside the code by simply using double asterisks. And that is another thing that's anomalous with Python. Other programming languages such as Java, JavaScript, you know, go on, usually have to pull in a special library to do exponents. In fact, you have to like, you know, call in the math library, call in the power library, put it into like a thing. You know, in Python, I think it's brilliant that they allowed it to just be a thing. So what they're saying is 10 times 2, right? That's a single asterisk, but the double asterisk, so it's really 10 times 2 to the 3rd power. Or this one is 10 to the 2nd power to the 3rd power, which you can actually do in math. Most people don't, but which is the equivalent of that. But it just shows you that it can be done. And so you can take an equation that looks really complicated like this. So it's, you know, we have not only, you know, a denominator and, you know, like a fraction here and multiplication, but we're also raising it to a power. Python pretty elegantly allows you to do that. Now, for my data analytics people, why this is important and why people like using Python to do data analytics work is because it is easy to write the equations and you don't have to often pull in libraries to write complicated equations. And, you know, it's not necessarily like if you're a programmer, like you're going to come up with the equation, chances are you'll be working on a team and some scientist or, you know it all or engineer or something will come in and say, here's the equation, code it, you know, and then it's your job to get it right. You know, so, and often those high level people typically learn how to code ultimately themselves. So, all right. Let's talk about some like weird math now. Math that you may never have encountered before that is unique to programming languages. So we have this concept of like, particularly when you do division, that you have the capability when you do division, depending on how you learned it. Like if I divide, you know, so we have this approach, right? The calculator approach. If I divide 7 by 4, I get 1.75. All right, so let's keep that number in mind. However, if we use what we call floor division, so let's keep this over here. In other words, we use 2 dividing marks together. This evaluates to whatever the whole number is, the largest whole number that fits inside there, disregarding the remainder. Okay, so think about that. So if I run this equation, it's really the same division, but I'm not looking for the 0.75. I'm only looking for the 1. All right. Now think about that, right? You know, if um, if you're like doing some math to figure something out, it's like there's certain things that you buy that you just cannot buy like a portion of. Like, like if I'm going to walk into the grocery store and buy like peanuts by the pound, I can sit there and scoop it and get it to like 1.6 exactly because that's how much money I have or whatever. Um, but if I go to buy a car, it's not like I can buy a portion of a car. So I might have almost enough to build another car, but it's still not a car. So you're looking for that whole value, and that's called floor division. It's done by using two slashes. It ignores the remainder. Conversely, we have this other type of division called modulus division. And the way that that one works is even a little stranger, because now we're not looking at the whole number, we're only looking at the remainder. So in that case, excuse me, if I do this mod symbol, and the mod symbol is the percent sign. So I am dividing 4 into 7, but I'm not looking for how many times it goes in fully. I'm looking for what's left over. Now, students always go, well, what's the point of that, right? Well, you know why they developed this stuff? It's always based on a practical thing. It was developed because people needed to figure out how to make change with computer programs or cash registers. And this cash registers do this, right? So like if you walk into a place and you buy something for 66 cents and you hand the person $1 and they have to make change. Okay, so how do you, okay, so if you ever worked retail, especially in the pre-cash register days like me, right? Somebody, you would have to like add stuff all up either in your head or on a piece of paper, and then somebody hand you a bill and you have to know like how much money to give them back. And it always floors me. Like I'll walk into like, I don't know, like McDonald's or something, right? And you give the, let's say the total is like $5.26, and then you hand the person a 10, and then, oh wait, I got 26 cents or something like that, or a penny, even better, and they don't know what to do. And I don't know if you guys ever encountered that, but it's kind of a trip to watch people fumble, because if they already punched in the $10 on the cash register, they have no clue how to do the math to figure out what coins to give you. Well, Modulus kind of solved that problem in terms of it looks at the piece that goes in. So like if you were to make change, you would start with a quarter first. Can I divide what's left over by a quarter? Okay, so I would say, well, with 66 cents, I have 34 cents left over. I can divide that by 25 and give them 1/4. But now I need to know how much is left over to get to the next step, right? So if I divide that in and the number is 34, how much is left? 9, right? So I need to know the remainder sometimes. So I would do a float division to say 1/4, and then I would do float division again to say you got 9 left over, and then I divide the next increment by a dime, because that would be the next largest increment. Right, and it's like, I don't know what mathematician sat down and figured all this stuff out just to make a cash register work, but somebody did. And the modulus division can become very, very useful in doing a lot of pretty sophisticated things. And they give examples here, and it's always usually dollars and cents examples. And so, yeah, basically they're just doing exactly what I just talked about, because it's such a classic problem. All right, let's move on. I think at this point, you'll have to get into the situation where you actually need it before you move on. All right, there are some other things that sometimes that are higher mathematical functions that you will need to actually call in functions from libraries in order to do the work. So this is an example of that. So what do you think this one stands for, ABS? Well, it's absolute value, right? So just define what absolute value is if you don't remember from your school days. It ignores whether a number is positive or negative. It just looks at its value, basically distance from 0. So, and in some cases that's important, because let's say if you want to do division with a number, you can't divide by the negative number, can you? You guys are thinking about that one a little bit, aren't you? But it's kind of interesting that there's all these different little things that you can do. So they have things where you can absolute value to get rid of the negative. There's also rounding functions, including rounding functions that round to specific decimal places. And they give kind of just like simple examples. And these are the ones that we start with. They also have these other pre-built functions, which we'll get to learn here just in the table below. So you can get absolute value, you can round, you can also find the minimum value in a list of values. And another common one is to find the maximum value in a list of values. Now, these are not the only mathematical functions out there, but these are some of the basic ones that you can get started with to do a lot of simplistic tasks. All right, moving on. All right. Now, Python and most languages do have some of these mathematical functions just built into them. However, there are times when you start reaching into higher level ones, and those require specialized libraries. So if you are using those specialized libraries, for example, to do a square root, you would have to add this statement to the top of your Python program so that the program knows to bring that library into the mix. It is one of the standard libraries. It is like part of the Python implementation. It's not like you're downloading it from the web or anything, but normally it's not loaded in because by loading it in, it can take extra memory that you might not want to give up and make your program inefficient. So what they've done is they use these, what we call import statements, to pull in the specific tool you need to do the work. It's like going to your toolbox and pulling out the right socket wrench, to fix your starter or something, and it's like a 10 millimeter. You can't use like a 3/8, because they're not the same. And so we're pulling in like a different set of tools. And then once we've pulled the tools in, then we can go ahead and use the tool. So some of the functions that you'll find in the math module, once again, this is a brief list, real common ones. So you see like trigonometric functions here, including logarithms, cosines, sines, and all that stuff. Another handy little chart here where they show you how to take some complicated looking mathematical expressions for common formulas. These are actually pretty common types of formulas, and how you actually convert them. Notice that pi has a built-in value. So if you pull in the math module, pi is pre-assigned. So you don't have to like create a variable that's like 3.1415 and memorize all that. It would pull the whole thing in. I think we're doing pretty good on progress here. I think we're approaching the point where I want to take a break here pretty soon. All right, so we're on this page here that talks about common errors. So you know what? I think to save time, I'll have you guys read some of this, but it does, this particular one talks about how you declare your numbers and the rounding errors that would equal. So this is kind of bizarre because if I put in 4.35 and 100, right, for these two variable values, and then I multiply them, right? I mean, that should be the answer, 435, right? I mean, it's a no-brainer because we're just moving the decimal place over. However, in Python and other languages, Python's not the only one, and it has to do with how math is done in the background. It actually resolves to really, 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 really close to 435, but not quite, and so, and the problem is with the underlying number structure that computers themselves use, which is the binary 0 and 1 states, and how those numbers convert to other numbers. And I mean, if you ever did any like advanced math, you probably learned some of this. But so sometimes there are, for example, it says like there's no exact representation for 1/3, right? In a fraction, it's easy to represent. In numbers, it's an infinitely repeating string. And those round off errors, can be a little perplexing at times, but you can also code around it at the same time. So there are workarounds for it. And I do have a little thing about it here. Always, if you are using parentheses, make sure you balance them correctly, that they're all, associated to what you need. That's what that one is about. The other thing is they recommend is when you're typing this stuff in, leave spaces between the characters, because visually that's easier for your eye to see and interpret. For whatever reason, would it not work if I squeezed it all together? It would work just fine. The computer doesn't care. It's our eyes that care. So this is a little harder to read than this one. And so they recommend use spaces. There are other ways to import libraries as well. For the most part, you should know what you're trying to import and import it directly. You want to import multiple functions. If you use the wildcard asterisk, you pull the whole math library in. That's kind of dangerous. You really can weigh down your program. But you can also do it like this. You can just say import. You can say from math import. So this statement and this statement are essentially the same. Now, part of those differences stems from like the evolution of the language itself, but that's a very common approach. When you're looking at languages like, I'm trying to think here, some languages will call them includes, some languages will call them using statements, some call them imports, but they're all functionally the same thing. You're just pulling extra resources in to use in your program. And basically what these are pre-coded libraries of instructions so that you don't have to write the code that creates the correct output. Somebody figured out how to create a square root thing, so we use it. We don't recreate it. All right. This next little thing, and I'm going to spend a little time on this because I think this is an important concept. And we have what we call these combination operators that are kind of unique to mathematics. And what I always tell students, if this confuses you when you first start to program, do it the longhand way. Don't do it the shorthand way. So somebody said, well, if I want to take a total of a value and add it to something I already have. So in other words, I'm really going, whatever cans is, I'm adding to total and then putting it back in total. They came up with this shortcut operator, which is plus equals. So this statement is functionally equivalent to this one. And so wherever you see that plus equals, that means I'm taking cans, I'm adding it to total, and I'm putting it back in total. Total plus cans equals total. Now, not to mess with your mind at all, but you can also do that with multiplication and subtraction and division. And I'll tell you, usually addition and subtraction are pretty easy to wrap your head around. When you start to do multiplication and division, it kind of messes with your head a little bit, because you're self-referencing and dividing upon yourself. So usually, most students will stick with the plus equals and the minus equals, for example. That's just, I think that's kind of interesting. The other thing that happens too is sometimes you're writing these equations and they get so long that they don't even fit on one line of code. So it says, if that's too long to fit on a single line, you can continue it on another line, provided the line break occurs inside parentheses. So for example, if I wrote this all in one line, I wouldn't need that parenthesis or this one. But because it's going to a second line, I'm just putting the whole thing inside of parentheses, and then you can split it onto another line all you want. Typically, I recommend try to stay on one line. We're not going to write any equations that are like that kind of long that we need to worry about it, but it's good to know. All right. I like some of these. I'm not going to cover this in detail, but you guys notice like a little theme here, right? And the author finally kind of gets to the point of like describing, I think, problem solving in a little bit more depth. But whenever you try to do a programming problem, it really helps to know what you're trying to program. And that's the whole point of like doing the pseudocode and the flow chart is to kind of rough out what you're doing in advance. And then when you have that as a guide, it's so much easier to build. And they go through a whole example here, and I'm not really too concerned about it, but feel free to explore. All right. So they also have these neat little things, you know, and actually I'm not going to spend any time on this either, but I think this is kind of a fascinating one. Talks about like how robots move and the time it takes to travel. Right? So I guess kind of what I'm saying with that is it's not part of your homework. Guess get what I'm saying. Why don't we do this? Can we take like a 4-minute break? I just want to refresh my beverage here really quick.
Yes.
And I will pause the recording and we'll come back.
Sounds good.